Thank you for giving me your attention for this talk on the EV Snapshot Imaging Spectrograph reflight. So this is a joint mission between two NASA centers and Montana State University, as well as American University. You can go to the next slide. Actually, one more slide. All right, so just to start off with a little bit of background of the ESIS mission, it has a lot of maybe heritage or relationship with its progenitor, the MOSES instrument, which is the multi-order solar EUV spectrograph, which was also developed out of MSU. MOSES flew 3 previous times. One of those times it actually flew with ESIS on the same optics bench. A lot of those missions were pretty successful. The core idea here being that you can take multiple projections of a multidimensional scene and use those various sets of data to reconstruct information about your original data volume. So here's a picture of the ESIS-1 team right before their 2019 ESIS-1 launch at Wismar. You can go to the next slide. So just motivating why we're interested in imaging spectrographs at all. Really, if you think about traditional slit spectrographs, one thing you have to do is raster your slit across an entire field of view to get your spatially and spectrally resolved image. That can take time, obviously, and it's a really good way to, for example, miss all of the action, like you can see here in this iris animation here, where the explosive event is just not really captured by any of the slit scans at the time. So with an instrument like ESIS, what we're hoping to do is to measure the spectral line profiles over the entire extended field of view in the time of a single exposure. You can go to the next slide. Let's see. And the science that we're targeting for this flight is active region science. We're trying to constrain coronal heating models. We're looking for signatures of E-beam heating events. And we really want to characterize those heating events. Where are they happening? How frequency? At what time scales they're happening at? We'd also like to actually quantify the magnitude of them and the low energy cutoff. Measure the intensity, velocity, and profiles of the transition region lines themselves. Another thing that we want to do for this mission in particular is validate our inversion methods. So maybe I haven't yet convinced you that we can actually obtain velocity profiles from this type of instrument. But one of the ways that we're trying to do that is to add more channels so we can have options for how we do that inversion and perform any validation. You can go to the next slide. So here's just a layout of the ESIS design. ESIS-1 is shown on top of ESIS-2 there. The basic idea here is you have light coming in from the left. You can see the gray ray traces on the bottom of ESIS-2 coming in, and they are reflected on the primary mirror there, which is blue in the top ESIS-1 image and gray in the bottom one. It then passes through an octagonal field stop and then is diffracted. Each channel gets its own diffraction grading, and you can see that kind of there in the oval at the bottom of the image there. Before then it gets passed on to one of the camera channels. So ESIS-2 is going to have 6 camera channels, where ESIS-4 or ESIS-1 only had 4. You can go to the next slide. Here we go. Here is kind of a footprint outline of what ESIS-1, the images ended up looking like. Another name for imaging spectrograph is an overlapogram, and you can kind of see that here, where your octagonal field of view gets overlapped with each of the prominent lines that are imaged on the detector. Go to the next slide. One thing that we're changing for ESIS-2, you can go to the next slide, please. Thank you. For ESIS-2, we're adding 2 more channels, as I mentioned before, but we're also confining our bandpass to make sure that we are choosing lines that have a little bit less overlap. This helps us, just kind of limit our spatial spectral confusion a little bit. You can go to the next slide. The lines we chose here, so the ESIS-2 passband is from 440 to 430 angstroms. We chose fairly bright and isolated lines. We have this neon 7 line that gives us access to about 500,000 degree kind of moss structures. And we have, we'll be able to image hotter loops with the silicon 9 line at about 2 million degrees Kelvin. So we've got these simulations that show us the signatures of these e-beam heating in that neon line. So we're looking for these blue shifts that gives us that telltale, these e-beam heating events. So that's kind of what we're looking for. If you go to the next slide, please. And just to kind of give you an intuition about how ESIS can capture some of those velocity signatures, you can imagine a monochromatic exploding point source, like is shown on the field of view on the left side of the screen there, kind of on the south of the field of view. And for each of your channels, depending on the direction of dispersion, that exploding event is going to be stretched out in a different direction. So the difference between each of these ESIS channels is the direction of dispersion. So in channel A here, you see the stretching is happening along the line of dispersion, and in channel B, it's also along the line of dispersion, but those are actually, opposite to each other. So when you take the difference image, you get this kind of X shape with these negative and positive lobes that shows you exactly where that explosive event occurred. If you go to the next slide. Alternatively, if you just have a monochromatic elongated structure that doesn't have a velocity component, that's going to end up looking exactly the same in both of those channels, with minor differences because they're different detectors, and you're just going to end up with pretty much a flat field from that difference image. If you go to the next slide. So intuitively, that lets you know, with just basically 2 channels of ESIS, you can do that level of investigation and find your explosive events and where they're happening and what kind of explosive events are occurring. So here's some data from ESIS-1. On the left is the field of view of the quiet sun that was imaged. And then on the right there is just the 4 channels being displayed all together. You can see the overlapogram nature of these images. Go to the next slide. And these should be little videos. I hope they are playing on your screens. Oh, yep, they look like they're playing on my screens. Good. Okay, so on the top left here, we have just what the raw ESIS data looks like. You can see all those prominent lines and their field of views and their octagons kind of overlapping. You take a couple of those channels, and you can do that kind of high-level analysis, right? You take the difference image, and you find all these exploding events. In the red boxes, you can see a few of those examples, and in the bottom left, we call out specifically the the types of events that's occurring. You get blue shift events that look like little upturned arrows, and red shift events that look like little V's, and broadening events that end up looking like X's, as I described in the cartoon. If you go to the next slide. So that's just with a 2-channel analysis. Obviously, if you apply all of your channels, now you can actually do a proper inversion method. You need at least 3 channels to do this type of inversion. For ESIS-1, MART inversion was applied. MART is multiplicative algebraic reconstruction. Basically, it enforces positivity, which is good because in this kind of imaging application, a negative photon doesn't make a lot of sense. It also makes no assumptions about what the solution is supposed to look like. So even though we suspect this should look vaguely Gaussian, we don't need to force that into the solution for the inversion to come out. So here's an example. This feature develops over time, and each of those red dots represents a point at which we could invert the velocity profiles, and MART was able to conclude the various shifts and line widths of each of those pixels. So for ESIS-2, we're adding additional channels, and this enables us to basically increase the fidelity of that inversion, as well as gives us more options for how we do the validation. This works pretty good, obviously, for these individual point source type explosions. For elongated events or elongated structures, we're going to have a little bit more spatial spectral confusion, so we want to be able to have all of those inversion channels at our disposal. Go ahead to the next slide. So for ESIS-2, we are changing a few of the things, obviously the passband, and this allows us, we've selected a multi-layer coding design that has really pretty high effective area, allowing us to have pretty short exposures. It's actually the maximum cadence that we can run our cameras at, a little bit over 1 second of camera cadence. We have these images are not fully updated. We actually changed our focal length a little bit. So imagine that simulated image on the bottom right is about zoomed in about a factor of 2, but that neon line is going to give us the mossy structures on the left side, and then the silicon line is going to give us those loop structures in the top. Imagine they're a little bit more zoomed in, but that's essentially what we expect to see. You can go to the next slide, please. And just briefly, I'll give you a little bit of an update about where we are with the design. The cameras and the avionics, these are the subsystems that Marshall is specifically on the hook for. We've flown these cameras several times. We call them like the ESIS 1 style cameras. We've flown them on ESIS 1. 4 of them flew previously. We also flew them on Kool-Aid, which was an instrument that rode along on High Sea Flare, and we flew them on FIRST. So we have a good bit of heritage with these systems. We're building 2 more cameras, and then we're going to validate and test them all. Fortunately, we built the cold block and mounting structures to support 6 cameras, so we really just need to test them all together. Once they're built, the electronics are built for these or in progress of being built, and the cameras should be ready for performance testing early next year. The avionics system, it's the same avionics that we flew on ESIS 1. We are updating it, though, to support EVTM for image downlink and for health and status, keeping some of our analog channels, so it's a little bit of a in-between step for us in terms of our avionics system. We've gotten ourselves into a little bit of a pickle with this. One of the ways that we save money is by sharing our avionics between different missions, and we have currently done that to ourselves with 2 other missions, the first mission and the MAGIX mission, which we should hear about later. So we are currently working on mitigation strategies to enable us to get back some of our schedule, as some of those missions might be delayed and impact our launch ultimately. But overall, the design of these systems is totally finalized. We're working on the software modifications to support those 2 extra channels. We have the hardware updates to go, but we can't do that until successful launches of FIRST and MAGIX. Next slide, please. So the instrument itself, so this instrument was originally developed at MSU and has been handed over to Goddard now, and the design is updated. So we're changing that field of view. We have almost 7 arc minute field of view and 0.45 arc second per pixel plate scale. With that entirely new design, even though the sizing and spatial footprint of the whole instrument is just about the same, almost all the elements are going to be updated. So we need a new mirror, different prescription, new coatings, new gratings with different prescriptions and line spacing, etc. The optics bench is the same. We just don't have Moses on it anymore. So the redesign itself is completed. We're moving to the procurement phase, and the optics should be out for delivery sometime in the spring of 26. So we hope, so that we can start getting alignment and getting the instrument integrated. So the launch has previously been scheduled for June of 2026. Of course, schedules are in flux right now, so we await to be updated with that information. You can go to the next slide. And I think I'm coming to the end of my time here, so I'll just summarize by saying that ESIS 2 will measure the Doppler shifts of the neon 7 and silicon 9 lines at about a 1.2 second cadence over a 6.8 arc minute field of view. The observations will be used to constrain the active region loop heating models and examine importance of e-beam heating. We're going to be adding those 2 additional channels, and that's going to allow us to validate our inversion methods. And measure the line profiles and spatially extended active region features. So we have a lot of work to be done. Other than that, thank you for your time.